Okay, so hello, good morning, good afternoon, wherever you are. And thanks for the invitation to participate in this conference. So the title of the conference Is Portland Cement the Problem? Personally, I'm not sure that's the right question. Maybe the question should be, is humanity the problem? And I think there the answer is certainly yes. And it's not just since the industrial age. People seem to have this idea that we were in this wonderful equilibrium with the earth before the industrial age. But if we go back, we see even 50 to 100,000 years ago, we'd managed to wipe out all the megafauna in Europe, and already in the Middle Ages, we ran out of wood. We had to stop cutting down forests, and that's when we turned to using coal. So it's been a long history of humanity really not being in equilibrium with the planet. And today people said, is overpopulation? Well, we do have a lot of people, but actually, when you look at the figures, it's the richest 1%, some 77 million individuals earning over 140,000, who are responsible for 16% of the budget and consume their entire carbon budget within 10 days. Whereas the poorest 50% of the population produce only 7.7% of emissions. So let's come back to the question and let's say, well, why do we use Portland cement? Well, the point is, this is an inevitable consequence, first of all, of the chemistry of the Earth. 98% of the Earth's crust is made up of just 8 elements: oxygen, silicon, aluminium, iron, sodium, potassium, magnesium. And to make a cement, what we need things that dissolve, and then they precipitate. They precipitate solids, which hold the whole thing together, which gives strength and durability. And in that terms, the oxides of sodium, potassium, well, they're too soluble, so they don't go into the hydrates. While on the other hand, the oxides of iron and magnesium, we have the opposite problem of too low solubility, so they don't contribute to filling the space between grains and holding grains together. Which takes us to the system of calcium, silica, and alumina. Now, then there's another issue which is important, which is down to geology. So geology is a very complex field, but from a very simple level, it boils down to this. We have volcanoes which produce rocks, and those rocks have on average the average composition of the Earth. And then we have a weathering process. And this weathering process effectively separates the rock into mainly the calcium-containing component, which reacts with CO2 in the atmosphere and forms calcium carbonate or limestone. And this process is facilitated by the fixation of oxygen in the oceans, the fact that many microbes use calcium to produce their skeletons. And this leads to these very rich and pure deposits of limestone all around the world. And this picture here shows you a map of the main limestone deposits in the world. And of course, because of this weathering process, whatever isn't limestone is all those other elements, aluminosilicate rocks, and eventually clay. So when we zoom in on Europe, we see this intimate mixture of lime and clay, and it's not really surprising that the technology of mixing these together in the good proportions led to the invention of Portland cement about 200 years ago. So 80% of the raw material to produce Portland cement is limestone, and of course then that becomes the problem, because we have this calcium carbonate, it gets heated up, it breaks down into calcium oxide and CO2, and that's responsible for about 60% of the CO2 emissions of cement. So what we've seen recently is a few startups saying, well, let's go back to these volcanic rocks like basalt, let's get out the amount of calcium they contain, and let's make the clinker with uncarbonated calcium oxide. Well, there's two problems to this. First problem, cost. Well, people always say costs can go down, but a much more serious problem is we look at the calcium content here, we see it's about 10%. That can combine with about 10% of the silicon, but that means that 80% of the material is reject. So if we use these processes to produce the cement we need, 4 billion tons, we would be producing 16 billion tons of waste. And that would just in one go double the amount of waste we were producing on Earth. An absolute environmental disaster, clearly. And I haven't got time to detail what are the problems with a lot of other solutions put forward. But, you know, they're either impractical, costly, unscalable, will take too long to mature, and have little or no possibility of delivering any significant impact by 2050, which is what we need to do. So, Portland cement, an inevitable consequence of the chemistry and geology of the Earth. And then we need to look at the materials we're using. This graph here shows by mass, volume, and CO2 emissions all the materials we're producing each year. You can see concrete makes up 3/4 of this total. So clearly, from a purely resource point of view, we can't replace it by anything else. But then when we look to the CO2 emissions, we see the CO2 emissions are quite low in proportion to this relatively large volume. Well, that's no reason to be complacent, because it also means if we can make it better, we have a huge possibility for CO2 reduction. And we can make it better. Now, where we've got to make it better, we have to take into account where cement is being used. In the last 40 years, the huge growth in cement was dominated by development in China. And China now produces more than half of the world's cement. But in the next 30 years, this situation is going to change again. Use in China has already started to decrease, and this is a normal phenomenon of growth. Here we see for all different countries plotted the cement consumption per capita against GDP per capita. You see all countries go through this maximum. China went through a really high maximum, but it has already been coming down for over 10 years now. And even if China continues to increase its GDP per capita, its cement consumption is likely to go down dramatically. Maybe 1,000 out of 1,500 plants in China will close before 2060. So more generally, there is a lot of good news because there's a lot of things we can do. We really need to take a holistic view to sustainable construction. First of all, we need to think, do we need to build at all? Can we renovate and therefore build less? And if we do build, can we build more cleverly and use materials more efficiently? And this consideration is very important because we do continue to have a demand for building. This shows the new floor area expected by 2060, and you see it's dominated by the global south, particularly India and Africa. Now, for cement-based materials, this shows the levers we can use to reduce CO2. And the point is 4 out of 5 of these levers can be implemented at very low cost, even negative costs. So we start with being more efficient in design and construction, using less concrete for the same building. That doesn't mean using other materials. It just simply means using the concrete more efficiently. Can we use less cement in our concrete? Yes, the answer is yes, usually. And can we use less clinker in our cement? And then in making the clinker, can we use alternative fuels and be more energy efficient? Now, all of these measures can have a very, very dramatic impact on reducing CO2 emissions. There will be a gap, maybe around 20–30%, which will have to be filled with carbon capture and storage. But this is where the cost becomes completely different, much, much higher. So putting that another way, if we take these 3 central things: reduce clinker in concrete, reduce cement in reduce clinker in cement, reduce cement in concrete, and reduce concrete in buildings. We see, as published here, we have potential to reduce something like 76% of emissions. And really, to push this efficient use of materials, we need to have good metrics. We need to look on the final building level, for example, what's the CO2 embodied per square meter? And this was a preliminary study done in Europe, which has now led to this Global Building Data Initiative, which we're piloting through Globe to have simple measures for evaluating CO2. And, you can see how important this is in this study we did on a low-rise apartment building, a typical building that's deemed to be kind of fairly optimal in terms of places to live. And we took this in, first of all, the concrete as usual situation where you have a concrete frames and you have fired clay bricks filling in the walls. And these fired clay bricks are a big problem. I mean, they're often produced in very inefficient conditions, as we see here in Tanzania. I mean, this is, terrible because they're using wood for firing, which is leading to deforestation. They're using topsoil, which is then affecting the ability to grow crops. So what we did here was to make this what we called eco-concrete, where we did low carbon concrete in the frame, but then we also put in concrete blocks. And then we compared this also with cross-laminated timber, with laminated veneer bamboo, and with concrete stabilized earth bricks. So concrete blocks, I think, have a huge potential for locking in CO2 reduction. This is studies going on in our lab in Lausanne, and you can see overall from the highest fire clay bricks to the lowest concrete blocks, we can have a reduction in emissions of tenfold. This is enormous. And this means that the eco-concrete house, in this example, we could halve the emissions. We look at the stabilized earth bricks, you can see they're actually higher, because when you start stabilizing earth with cement, it's a very inefficient use of cement, and it has higher emissions even in the reference case. And then in the middle, these two bio-based solutions, well, you can see then there's a lot of controversy about how you should account for the CO2 emissions. Do you just account for the processing emission? Do you account for stocking the CO2 in the wood, which is interesting, but what many of these calculations don't do is account for all the waste, all the harvesting-induced emissions, which is probably a better way of doing it. And so you can see with the kind of more realistic harvesting-induced emissions, these have higher CO2 emissions, again, than the concrete solutions. And even in the unrealistically favorable situation here, you're really not better than the eco-concrete. And of course, eco-concrete can be done everywhere, whereas only some parts of the world have good access to timber and things like that. So coming back to this waterfall here, we see there's this huge potential, and it's the central one replacing clinker and cement, which really has the tremendous potential. It's comparatively easy to implement. And of course, it's not new. We've been using substitute materials like slag and fly ash for many years, but the problem of these classic substitutes, slag and fly ash, is the amounts available are relatively low compared to the demand for cement. Slag, we have something like 8% compared to cement, and fly ash probably even less, because a lot of it's unsuitable. And of course, fly ash comes from burning coal, which is the #1 thing we have to do to confront climate change. So this led to the solution LC3, where we replace half or even more of the clinker by a combination of calcined clay and limestone. And these combinations can have similar strength to reference Portland cement, 40% less CO2 emissions, and much better resistance to chloride and alkali silica reaction. And this is because calcined clays are very reactive, pozzolan, much similar to slag, much more reactive than fly ash, and natural pozzolans. And this reactivity comes from their layered structure, also for these one-to-one clays, kaolin. When they're heated, their structure becomes disrupted, and both the silica and alumina can react to give space-filling hydrates. And these kinds of clays are really available very, very widely in the world, particularly where we're seeing this growth in demand. So, okay, up in Scandinavia, you probably haven't got very much clays, but, to be honest, you haven't got many people up there. So the demand is not as strong there as it is in the middle parts of the world. And in 10 years, we've seen this LC3 product go from a few demonstration houses to these full-scale applications here in Colombia. All the cement produced from the Rio Claro plant of Argos for the last 7 years has been containing calcined clay. It's been used in all these applications, flyovers, shopping centers, everything. Also in Europe, we see examples, notably in Switzerland. This building has been built about 10 minutes from my office, and we have this brand new Rolex campus, which is under construction. So these are the factories which are in the process of adopting calcined clays. You can see it's really very widespread throughout the world, and the world potential is really huge. This is the level of substitute materials, how it's evolved in the past couple of decades, and the stagnation in the last 10 years has been due to this lack of slag and fly ash. If we remove that limitation, we could easily go to a 40% substitution, which would be 400 million tons of CO2. Or probably we could actually do twice as well as this with a bit of improvement in technology. 800 million tons of CO2 is like 2% of entire world emissions today, and something like 20 times the emissions of a country like Switzerland. So the potential is really enormous. It's really, as I said, starting to take off. We have now an installed capacity of 50 million tons, a long way to go to the potential of 400. And so far, we've saved 10 million tons of CO2, but the potential is well over 500 million tons a year. And all of this, really, the reason it's been taking up is cost. It makes business sense. And that's what's going to drive any technology, because I'm sorry, in many countries, there's no real pressure to reduce CO2. But let's not stop there, because LC3 is not the end of the story. We have to also think about reducing cement in concrete. And here there's also tremendous potential. This paper published 15 years ago showed the tremendous inefficiency of many concretes, which use 3 or 4 times as much cement as needed. And one of the ways of improving efficiency is to go from site mixing to ready mix industrial production. What we don't want to do is start doing 3D printing, which is unfortunately what many people are doing, which just increases emissions. So, let's stop these crazy ideas that really go in the wrong direction. This is more data showing the same thing, that the world average today is around 300 kilos of CO2 per meter cubed of concrete. We could quite easily reach a level of something like 100 kilograms per cubic meter. So we could cut in 3 the CO2 emissions from concrete. And reducing concrete in buildings is about simple, efficient design. This looks like a banal building, but, nothing's lining up. And the consequence is that here you see what's called a transfer slab, a huge, great lump of concrete just to compensate for the poor design of the building in the first place. And this is causing overconsumption of concrete. So that's the levers we have. We can do a lot. We need some support from research. This paper we published in Rhineland Technical Letters a couple of years ago. We made this watermelon, as we call it, to really highlight those areas where research was needed. And, I just want to stress again that we do have this potential to make substantial reductions. The problem is not Portland cement. The problem is the way we're using it, and we're not looking at how we can use it more efficiently. And this means we've got to work at all the different levels, the cement level, the concrete level, the structural level. And to do that, we need to get the industry working better together. This is behind the launch of the Globe Consensus from 6 professional societies, RILAM, FIB, CIB, etc. And, really, I think this is where we need to look to find actions that can help us implement these CO2 saving technologies today. And with that, I'd like to thank you and hope maybe later on we get some chance to answer questions. Bye.